These are the Lesson 9.2 notes on reciprocal functions. Today we're going to graph reciprocal functions and their translations. What is a reciprocal function? Well, basically a reciprocal function is a function in the form y equals 1 over x. And we're going to be basically graphing equations that have an x in the denominator of a fraction. We're going to start with a graph of y equals 9 over x. To graph this function like any function, what you could do is you could plug in different values for x and see what you get for y. Some easy ones I think you can crunch out in your head would be things like plugging in 1 for x. 9 over 1 is equal to 9, so there'd be a point at 1 comma 9. If you plugged in 3 for x, y would equal 3, so 3 comma 3 would be a point. And if you plugged in 9 for x, 9 divided by 9 is 1. So these are some common values that you would probably choose. Sometimes what you forget about, though, is plugging in negative numbers, and I think you could do some of this mental math with negative numbers as well. If you plug in negative 1 for x, 9 over negative 1 is negative 9, so there would be a point at negative 1, negative 9. If you plugged in negative 3 for x, 9 over negative 3 is negative 3, so negative 3 is a point. And if you plugged in negative 9 for x, 9 over negative 9 is negative 1, and this would give you this point. And you're probably thinking, what kind of graph is this? Well, this graph is going to end up being something called a hyperbola. And a hyperbola is a graph that actually has two separate branches. Why are there two separate branches here? Because if you try to plug in 0 for x, 9 over 0, well, that's undefined. You can't plug in 0 for x. You can't divide by 0. So there's no point at 0. And what this gives you are two separate branches to this graph. A branch that's down here, it kind of starts close to the x-axis, goes through our negative 9, negative 1 point, through negative 3, negative 3, and down here. And then this graph is going to continue down forever and ever and ever. And then when it hits 0, nothing happens. And then immediately, as soon as we get into our positive x values, the graph jumps up here. And it's going to do a very similar thing this way, like this. This graph has two asymptotes. Both the x-axis and the y-axis are asymptotes. So you could say x-axis and y-axis. Remember, the equation for the x-axis is y equals 0, and the equation for the x-axis, or the y-axis, excuse me, is x equals 0. Symmetry. This graph has two lines of symmetry. This line here is the line y equals negative x, and that would be a line of symmetry. There's also a line of symmetry that goes this way, and this is the line y equals x. So there are two symmetry lines, y equals x and y equals negative x, that are lines of symmetry for this graph. Now you can verify this on your calculator as well. If we turn our calculator on, first of all, I would clear out anything that's in your y equals menu. I would make sure if you go to second y equals that you have nothing in your stat plots that's on. I do right here, so I'm going to go to number 4, which is plots off, and turn all my stat plots off. And for your window, we want to use a standard viewing window using our negative 10 to 10 window for our mins and maxes. When you type this in your calculator, all you have to do is do 9 divided by x, and you'll see that we get our graph that matches what we just came up with. Now what about for 6 over x? 6 over x is a very similar graph. Again, you can do, I think, some mental math to figure out some points on our graph. This graph would go through points like 1 comma 6, because if you plug in 1 for x, you get 6 for y. If you plugged in 2 for x, you would get 3 for y. If you plugged in 3 for x, you would get 2 for y. And if you plugged in 6 for x, you would get 1 for y. These are some common points this graph goes through. You could type it in your calculator. You could do 6 over x. The graph gives you an indication of what it looks like. It looks like almost the same graph we had last time. In your table, if you go to second graph, if you're getting goofy values that aren't really practical, remember you can go to second window, change your table start to something like 0, and make delta table, what your values go up by, change it by something up like by 1. Go to second graph again, and you can see points like 1, 6, 2, 3, 3, 2. In fact, if you wanted to graph 4 comma 1.5 and 5 comma 1.2, you could do that. I tend to stick with nice integer values, nice points that go through these intersections of grid lines. And based on our points, obviously it's a different graph. but it is the same shape as our last graph. And just like before, we do have these negative values as well. You can verify these on your table, but I think it makes sense that you would see this graph going through points like -6, -1. 6 divided by -6 is -1. 6 divided by -3 is -2. 6 divided by -2 is -3. 6 divided by -1 is -6. So different points with the same shape graph we had before. It also has the exact same asymptotes we had before. You can call it the x-axis, y equals 0, and the y-axis, x equals 0. Same asymptotes, or same lines of symmetry that we had before, are y equals x and y equals -x lines. The parent function for all these graphs is the graph y equals 1 over x. Now, what values can you plug into this equation? Well, obviously 1 comma 1 would work. But then you get into goofy things like, if I plugged in 2 for x, I would get 1/2. Vice versa, if you plugged in 1/2 for x, you would get 2 for y. This is it's not as wide of a graph as we had with the other two. It's harder to see points. You can verify this on your calculator. When you do 1 over x, it's hard to see much of this graph on the calculator because most of the points are very close to one of our two axes. But this graph does have the same asymptotes as our other graphs do, the x-axis and the y-axis. I'm doing a very lousy job making this graph look right. It does not kind of bow in like this. But it's kind of hard to make these graphs because it is so close to this x-axis. Again, we don't want to actually hit the x-axis. So we do the best we can. It does go through these points. You do want to make sure that this graph goes through these integer values at 1, 1, and -1, -1. Same asymptotes we had before. The graph gets really close to but never touches the x-axis or the y-axis, and the lines of symmetry are still y equals x and y equals -x. As we move to the next example, what I'd like you to do is I'd like you to try to graph y equals -9 over x. List where the asymptotes are, and show me some nice integer values that this graph goes through. Pause the video and we'll see if your graph matches up in just a moment. So for our graph of y equals -9 over x, you'll notice that this graph has branches in the second and fourth quadrants, in the upper left corner and the bottom right corner. This graph should go through some nice values like -1, -9, -3, -3, -9, -1. Should also go through values over on the right side at 1, -9, 3, -3, and 9, -1. Be sure to show those nice intersection points that contain integer values for x and y. This graph has the same asymptotes as our other graphs do. Asymptotes are x equals 0 and y equals 0. So we still have this vertical and horizontal line that these graphs never cross. But it is in different quadrants because of this negative sign here. For the graph of y equals 1 over x plus 2 plus 3, you'll notice I've put parentheses around the denominator. To explore what this graph looks like, I want to make sure that when I type this in my calculator, because we're involving addition or subtraction in the denominator, I want to make sure that we include that in parentheses to make sure that that whole denominator, that whole x plus 2, ends up in the denominator for our calculator. And when we type this in your calculator, you're going to get probably one of two graphs depending on what model of a calculator you have. Some calculators may show that this looks like one continuous graph that connects right here. This is not really realistic. This graph is actually kind of showing the asymptote here. Other calculators may show a graph that maybe looks a little bit more like this. In any case, something goofy is happening around -2, which makes sense because if we tried to plug in -2 into this equation, you'll notice what we would get is we would get a 0 in this denominator because -2 plus 2 is 0, and we can't divide by 0. So this graph actually has an asymptote here at -2. I'm going to put a little dashed line on my graph at -2. This graph also appears to kind of level out not along the x-axis, but it appears to level out right around 3. And that's also an asymptote as well. And it kind of makes sense because if you look at the equation, we do have a -2 would give you a 0 in the denominator. But then there's this plus 3, which we usually assume with being a positive or kind of an upward direction. if we look at our table for nice integer values, this graph doesn't have very many. There is a nice integer value at -3, 2, and there is an integer value at -1, 4. You'll notice the calculator does say error at -2. That's usually a good indication that there might be an asymptote there. So I'm going to plot the two nice values that our calculator tells us. -1, 4 is over here. We'll put a dot there. We'll also put a dot at -3, 2, which is right here. This graph has the same branches that our other graph did, kind of these same branches that approach different lines. But what we say is that this graph has been translated. So we'll try to kind of draw our graph in here. And we'll add this branch right here. Your calculator doesn't often do a great job of showing this entire graph, so that's why I want to make sure that our graph actually mirrors what's really going on. This graph does not have asymptotes at x equals 0 and y equals 0. This graph has an asymptote that crosses the x-axis at -2. So we say there's a vertical asymptote at x equals -2. And we say there's a horizontal asymptote that crosses the y-axis here at 3. So y equals 3 is the other asymptote. So what I'd like you to try to do is I'd like you to try to graph this last graph here using your calculator and using good points that have nice integer values. See if you can find the asymptotes and a nice sketch for this graph. Pause the video and we'll see what you come up with in just a moment. So here we have our graph right here. Notice that we have 6 divided by parentheses x minus 2 minus 1 in our calculator. You can see our graph of our function. Some of your graphs may actually connect this right here, and that's fine. You'll see that this graph has 2 branches, and it does go through some nice integer points. Your calculator can verify some of these values like 8, 0, 5, 1, 4, 2, 3, 5. So we want to show that. Your graph should show asymptotes, and I want to see them denoted by these dashed lines here. -1 means we're going to have this graph have an asymptote that's down 1 on the crossing the y-axis. So y equals -1 is an asymptote. Because it says x minus 2 here, x can't equal 2, so it would be a vertical asymptote at x equals 2. And we can't plug in 2 for x because we'd be dividing by 0. That's why there's this vertical asymptote here. So we say the asymptotes are x equals 2 and y equals -1. So I think you get the idea of how to find asymptotes based on your equation, and the last thing you'd be doing today is writing equations for various translations. In the first problem, it says give equations for translations of y equals 1 over x with asymptotes at x equals 3 and y equals 2. Well, I've already noted in the other problems here that if you have an asymptote, for example, that's at x equals 2, that means that in the denominator of our fraction, we'd have something like x minus 2, because if we plugged in 2 for x, we'd be dividing by 0, and our graph doesn't have a value at 0. So the x equals 2 is going to be kind of in this part. And then if there's an asymptote at like y equals -1, that number kind of stays the same, but it's kind of attached to the end of our equation. So the x equals asymptote is sort of the opposite. If it says x equals 2, it's going to say x minus 2 in our equation. Again, if it said x equals -2, it would be x plus 2 in our equation. But then if there's an asymptote at y equals something like 3, we attach a plus 3 at the end, or -1, we attach a -1 at the end. So the same idea is true here. If it says x equals 3, using our other equations as a model, we would start with y equals. If we're translating 1 over x, we're still going to start with 1 over x. But then for x equals 3, we're going to go -3 right here. And for equals 2, we're going to do plus 2 at the end. And if you wanted to verify this on your calculator to see if this looked right, you could do 1 over x minus 3 right here. And then you could do plus 2 at the end. What I'd like you to do is I'd like you to see if you can solve the last problem with x equals 4 and y equals 0. We'll pause the video and check out your answer in just a moment. For our last equation, y equals 1 over x minus 4 plus 0, you could also just write y equals 1 over x minus 4. And to verify that this graph actually works, you could type it in your calculator, and you'll notice that this graph would have a vertical asymptote here at 4, and it does have this horizontal asymptote along the x-axis, which is y equals 0.